So wow. The point of these lectures is going to be to give an introduction to calibrated geometries. And so those of you who are well aware of this subject will be really bored because I'm going to start at the beginning and I hope take you pretty far, at least far enough so that the literature, which is now extensive, and that includes a lot of survey lectures, will be easily available to you. My plan is today to talk about calibrations in great generality, what calibrations are, what the properties of calibrated subvarieties are, and a bit about compactness properties and so forth. Then tomorrow I want to discuss the hardcore cases, the exceptional cases that arise in G2 manifolds and Ricci flat Kähler manifolds and spin 7 manifolds. And then on the third day, I want to talk a little bit about the global structure, deformations, the moduli space of special Lagrangians and associative submanifolds. And I'll also talk a little bit about the relationship between spinors and calibrations, which is a very pretty one and sort of unifies the outlook. Okay, so to begin, let me just take a philosophical point of view. The way Reese, Harvey, and I originally thought about this when we came up with it was that geometry usually in this day and age differential geometry is described by talking about a manifold, and then on that manifold you have some kind of tensor given, some sort of smooth structure. Right? You can have a metric tensor or the J associated to a holomorphic structure, or in the symplectic case, or given this symplectic form. But the Greeks didn't think this way. I mean, they thought about geometry as objects and curves and surfaces and, well, at least planes and lines, right? And in some sense, all modern geometries can be thought of from this point of view as well, sort of for every smooth tensorial presentation of a geometry, there are subvarieties which also capture the geometry. So if you think of Riemannian geometry is presented with this Riemannian metric, but it has a family of distinguished subvarieties, namely the geodesics. Right? And if you know the geodesics, you really know the structure of the space. And once you see that, in fact, it's easy to generalize the notion of Riemannian geometry to sort of length spaces, and this has been done. In complex geometry, the special subvarieties are the complex subvarieties. And in algebraic geometry, the special subvarieties are the algebraic subvarieties. And that, in fact, is exactly the concept of a scheme. I mean, a scheme is just looking at an algebraic variety as consisting as an object, all of whose points are really the complex subvarieties, the irreducible complex subvarieties of all dimensions. Okay, so from that point of view, one might ask the question, what are the subvarieties associated to exceptional geometries, to these manifolds with exceptional holonomy that you're going to hear about tomorrow? And the answer is the calibrated subvarieties. So, so just to be rough, let me say that what we're going to look at is always first-order conditions. Okay, so these are always first-order conditions, and so let's suppose X is a manifold, a smooth manifold of some dimension. Then you can look at the fiber bundle over this space, whose fiber at every point is the family of p-dimensional subspaces of the tangent space. So this is the Grossman bundle of oriented tangent p-planes. Right, the fiber above each point is all the oriented p-planes in the tangent space at that point. Okay? And now, given such a creature, let's suppose I take, sitting in here, some subset. At the moment, it can be any subset, right? Then, this is sort of any subset. Then you can define, you say that a C1 submanifold, an oriented C1 submanifold, sorry. So, an oriented C1 submanifold sitting in X is a G manifold if the tangent space, the oriented tangent space, I'll indicate that it's oriented by putting an arrow over it, is an element of G for all points in M. Okay? Very simple idea. Just take any subset of this bundle of oriented p-planes, and then a submanifold will be called a G-manifold if its tangent space belongs to this. This is a first-order condition on submanifolds. And most of the geometries that you know about, well, lots of the geometries you know about are of this sort. For example, complex submanifolds are simply those whose tangent planes lie in the subset consisting of the complex subspaces. Here, the P is necessarily the real dimension is always 2, and complex subspaces have canonical orientations. If you have a symplectic manifold, then there is a notion of Lagrangian submanifold. I'll talk about Lagrangian planes. I'll talk about that tomorrow. In contact manifolds, there are Legendrian planes and so forth. So there are lots of canonical examples. But notice that geodesics do not fall into this category. Geodesics are defined by a second-order condition. And if you think about surfaces which are minimal surfaces, surfaces that locally minimize area, then these are also not defined by first-order conditions. They're defined by second-order conditions. The minimal surface equation requires 2 derivatives. But what we're going to look at will be first-order conditions which have the property that they imply second-order conditions. Namely, they imply the minimal surface equation. And that's going to be one of the things we do. All right, so now let me start with some basic ideas. So let's let V be a real vector space, finite dimensional, with an inner product a positive definite inner product, which I'll denote this way. Okay? And then associated to this, I can define GP of V. So this is very much the same thing. This is the set, by definition, the set of oriented, well, I should write this out, oriented p-dimensional linear subspaces of V. Okay? And now there's also, we can also consider the pth exterior power of V. Okay, this is simply another finite dimensional vector space associated to this, and this carries a natural inner product. So there's a natural inner product on this space, which is defined on simple vectors as follows. If you have a pair of simple vectors of length p, so this is a wedge product of vectors from V and another wedge product of p, then this is simply defined to be the determinant of the p by p matrix whose ijth entry is the inner product of Vi with Wj. Okay, so that's a p by p matrix. You take its determinant. And now this, one can see is, one can see here that this is an alternate, that this is well defined well, that this sort of extends to this is skew symmetric and multilinear, and so it actually extends in each of its factors, so it extends to be a bilinear form on the entire wedge product. Okay? And the norm I'm going to write this way with a single bar. So this is just oh. I see. I guess that doesn't get used very often. All right, so I'll leave this down. All right, so now here's a basic fact. This Grossman space embeds into the unit sphere in here. So a basic and important fact is that there exists a smooth embedding okay, so into the unit sphere in wedge P. And this embedding associates to any, if I have an oriented plane of dimension P, this simply associates to it the element V1 up to VP over the length of V1 up to VP, where this is any oriented basis, is any oriented basis of Q. So you just take a basis of the subspace and take the wedge product. Okay, but the basis has to agree with the orientation, has to be the orientation, or represent the orientation. Now it's, of course, if you choose another such, if W1 through WP is another, then of course W1 up to WP, well, then each Wj is a certain sum, Aj, k, Vk, k equals 1 to P. And if you call this matrix capital A, the wedge product is just the determinant of capital A times V1 up to Vp. And this determinant is positive, because that's what it means to have a consistent orientation. Okay? They represent the same orientation if the determinant of the matrix of the change of basis is positive. Okay, so this is a well-defined element, and in fact, it gives you so. And it's onto the set of simple vectors. It's onto the set of unit simple vectors. Okay? And the orthogonal group acts on this space. It acts transitively. It's a nice manifold. But now the reason I'm doing this is that I want to think about a norm on the space that corresponds to this geometry, that really singles out the the simple vectors. So there's something called the mass norm, on this vector space, which is not the L2 norm, okay? Which is not the L2 norm. And the mass norm, there are various ways of writing it, but we don't have to worry very much about it. So I'm going to simply say that the mass norm has the property that the unit sphere the unit ball, is equal to the convex hull of GP. Okay? Now, I mean, this is going to be something with interior because the simple vectors give you a basis for the space. Okay, so it's not difficult to see that and for every vector you get minus the vector. So this is something which is certainly a good unit ball, but it's certainly not smooth, right? The unit ball is going to here you are in the sphere, and you have this very relatively thin subset, right? The dimension of the Grassmanni is much smaller than the dimension of this vector space. And so here's the Grassmannian, and then you're kind of taking the convex hull of this, whatever that looks like. It's some solid whose extreme points are the simple vectors. Okay, whose extreme points are the simple vectors. And so the geometry, in fact, of the convex hull of the Grassmannian is very pretty. Right. Again, the orthogonal group acts on it, but it's not so simple as you might think. Now, the reason for introducing the mass norm is what we're really interested in is the co-mass norm. So suppose I have an element which is in the dual space to our vector space, just a linear function on this vector on this. Now, this is, of course, nothing but the pth exterior power of the dual space of V. All right. Then on the dual space, there's a dual norm called the co-mass norm. Okay. So the co-mass norm of phi is given as follows. So I'll write it this way with 2 bars. And this is by definition the sup of phi applied to xc for all xc in GP of V. Okay? So this is the co-mass norm. This is a norm on the dual space. And again, it's something which sees the simple vectors in a very special way. Okay? Now, one thing to observe is that the co-mass norm is always the co-mass norm of phi is always less than or equal to the Euclidean norm, the usual L2 norm. And that's because if you think phi is simply equal to the sup of phi applied to, well, what should I call this? Eta for all eta in the unit sphere. Well, for eta in wedge PV, eta equals 1. So here you're taking the sup over of this on all unit vectors, and here you're only looking at the simple ones. Okay? So certainly this has a chance of being bigger, and you'll see that indeed there are many interesting times when this is not at all an equality. We're going to see that there are linear functions which have the property that they have many components which are orthogonal. So they're Euclidean. So the Euclidean length is huge, but nevertheless, whenever it sees a simple vector, it gives you a number less than or equal to 1. Okay. All right. So now, once you have such a thing, then you can define an associated subset, and this is what we're going to be doing all along. Associated subset. Sorry. Let me make an assumption here. So let's suppose that the co-mass of a given linear function is exactly equal to 1. Then you can define g of phi to be equal to the set of simple vectors the set of oriented p-planes where equality is satisfied. And this is the sort of Grossman manifold of phi planes. Okay. So this is fairly fairly straightforward and simple idea. In order to generate these subsets of the Grassmannian, here's a simple way to do it. You take a linear function. You assume that its comass is 1. If it's not, you can always rescale it so it is. Okay, and then you look at the set where it actually assumes it's. Now, generically, if you take a random choice, you're going to get exactly 1 point in this set, and it won't be very interesting. The name of the game here is to find those forms where this thing is actually big. So we're looking for the diamonds in the sand, the interesting forms. But when you find them, then they tell you something nice. Okay, now if we go back to manifolds, so here we are. So maybe I should leave that up there. So let's go back to manifolds. Okay, then if X is Riemannian, then we have this nice bundle, GP of Tx, sitting in wedge P of the tangent bundle of X. All of this sits over X. Okay? So now I can think of this bundle I was discussing before, the bundle of oriented tangent p-planes, as a subset of the unit sphere bundle in wedge P of Tx. And since it's Riemannian, we have the Riemannian inner product here, and we also have the mass norm, and on its dual space, the comass norm. Okay? So suppose I'm given a differential form, at least C1. So a smooth section of wedge P of the cotangent bundle, so an exterior P form, then this thing is called a calibration. It's called a calibration if two things hold. First of all, at every point, the comass norm should be less than or equal to 1. And secondly, this form should be closed. This form should be closed. Okay? Very simple. And whenever you have this, then you can define this subset so we have G phi, a subset of GP of X, and this is simply defined pointwise as we define that. At any this is again, it's not a fiber bundle in general, but this is the subset above each point of those oriented p-planes where you have equality, just as I defined here. Okay, and then definition, a C1 submanifold, an oriented C1 submanifold, M in X is a phi manifold if the oriented tangent plane is in this set for all points in the submanifold. So that's what we mean by a phi manifold. Okay. Now this must seem like the sort of height of nonsense, right? First of all, it's so simple and simple-minded. But as with many things in mathematics, we sort of figure these things out backwards. From a few examples, you get the general principles, and then you go forward again. Okay, so and the reason that, even though this is a very simple definition, the reason that it's interesting is the following. We don't seem to be making much of an assumption, but there's this amazing theorem which holds in this generality. And the theorem says that, well, the short form of it is that phi submanifolds, if phi is a calibration, then any phi submanifold or phi manifold, I guess I call it, is homologically mass minimizing, homologically volume minimizing. Volume minimizing. By the way, these things are also said to be calibrated manifolds, calibrated by phi. So another, also called calibrated submanifolds, calibrated by phi. So any calibrated submanifold is homologically volume minimizing. What do I mean by that? So let me make this more detailed. So, i.e., if M is compact phi manifold with boundary, then, and if I have another submanifold, M prime, okay, is any other compact oriented C1 submanifold of X with the property that it has the same boundary. So first of all, the boundary of M prime is equal to the boundary of M, and M minus M prime is 0 in real homology. It's the boundary of A for some real P plus 1 chain A. Okay? So the picture is simply this. Here's the manifold M, and then I have another manifold, and it's oriented, so I'll put an arrow on it. And now I have some other manifold, M prime, with the same boundary, but I'm requiring a little bit more, not just that M minus M prime be a cycle, but that this cycle actually bounds something. But what it bounds doesn't have to be a submanifold. It can be something quite weak. All I really have to know is that this cycle is 0 in real homology. Okay, so for example, it can be not 0 in integral homology. It could be something which, in the real projective plane, you could take. You could let this be 1/2 of the curve that generates pi 1. Pi 1 is a group of order 2, and this could be going around the other way. and the difference is. Okay, so so the conclusion is that then the volume of M is less than or equal to the volume of M prime. Okay? The volume of M is less than or equal to the volume of M prime. Furthermore, and moreover, there's another interesting fact, and that is that if the volume of M is equal to the volume of M prime, then M prime is also a phi submanifold. The only way you can get equality is with another phi submanifold. The only way you can get equality is with another phi submanifold. So let me give you the proof. The proof is really 2 lines. And in fact, I mean, this proof and this whole sort of concept really goes back to Herb Federer, who did it in the Kähler case and used it in the Kähler case. And I think he, in some sense, used it as a general tool from time to time, but he never sort of explored geometries with it. But, I mean, here's the proof. It's very easy. because this is a closed form, if I look at the integral of phi over m minus m prime, this is the integral over the chain m minus m prime. Now this is the boundary of a real chain, and we know that this is the same thing as integrating over a d phi. Okay? And that's 0. So that means that the integral, if you have 2 homologous manifolds, and that's then the integral of this closed form over m is the same as the integral over m prime. But now we have the fact that that phi restricted to m is equal to the volume form of m, right? That's the definition. I mean, I should say, I can't pull this down. An alternative form of this an alternative way of making this definition is to say that, notice that M is a phi manifold if and only if phi restricted to M is equal to the volume form of M, right? Because this simply means, what is phi restricted to M? Phi restricted to M is phi applied to the unit simple tangent vector at M. Okay, that's another way of thinking of it. Phi restricted to M is the same thing as phi applied to the unit tangent vector to M, and then to the unit tangent space, and then d vol of M. Okay, this is a basic fact. And so exactly what happens is that you have a phi manifold if and only if this is true. So maybe I should write that down here, and then so phi restricted to M is equal to phi applied to the unit tangent vector times d times the volume of M. And this is, because this is equal to 1, this is just the volume form. And now the same thing when restricted to M prime, this is phi, the volume form of M prime, and this is less than or equal to the volume form of M prime. Okay, so now you take that equality and you plug in, And you see that the volume of m, which is equal to the integral over m of phi, is equal to the integral over m prime of phi, and this is equal to the integral over m prime of phi applied to this d vol m prime, and this is less than or equal to the volume of m prime. But furthermore, you're only going to get equality here if this is 1 everywhere, because this is always less than or equal to 1. So equality holds if and only if phi is equal to 1. Okay? All right, this is a smooth submanifold, so. And that's it. The proof is shorter than the theorem. But it's incredibly important. So it has a lot of consequences, this theorem. And so one of the first consequences is that any phi submanifold which is class C1 is actually much smoother. Because, well, maybe I should say the first consequence is that, well, no, I guess I should put it this way. So consequence is, if you know that X is a manifold of class CK, where K is anything between say 2 is less than or equal to K. It could be infinity or even real analytic. Then M is CK. And this follows from the regularity theory for minimal varieties. Regularity theory. Goes back to Charles Morey, for example. So if you're working in something like a complex manifold, then these things are automatically real analytic. Even though you start with them as just class C1, they're automatically real analytic. Okay, and they certainly satisfy the fact that they're minimal surfaces, so the mean curvature is identically 0. And in addition to this, there are certain monotonicity properties. So let me say what I mean by that. So any such manifold is smooth, it's minimal, and by oh no. If it won't stay down, then I'll just write on this.
You meant to write that if M is C1, then it's CK? Is that M was C1?
If it's C1, yeah, I'm assuming M is C1. Yeah. So what are the monotonicity properties? So in the case of Euclidean space, what's true is the following. Suppose that the boundary of M intersect the ball of radius r about the origin is empty. So you've got a submanifold of the ball of radius r, and it's without boundary in that ball. Okay? And let me make this a capital R. Okay, then you can take the volume of M intersect the ball of radius small r about the origin and divide by r to the dimension p. And this is a monotone increasing function in R. It's a monotone increasing function in R. It's so, for example, this means that you can't have, this is a general property of first variation 0. You can't have a manifold that's long and thin. Doesn't work. It's got to grow. If you take a point on it, so let's assume that this is true, then it's got to grow. Its volume has to grow at least as fast as that of a Euclidean disk of the same dimension. And it's common to actually put here the volume of the unit ball of radius 1, of dimension p, and then what happens is that as r goes to 0, this decreases. This has a limit, and that limit is called the density. Now, of course, if 0 isn't on the manifold, you get 0. But otherwise, you get the limit of the volume of M intersect. Well, maybe I'll put this there. So if you take the limit of this volume of M intersect the ball of radius r about the origin, divide by alpha p, r to the p, as r goes down to 0, this is going to be 1. That's not hard to see for a submanifold of class C1. So this means in particular that the volume is always bigger than that of the unit disk. Okay? So there's a lot you know about anything that satisfies first variation 0, and much more when you know that they're actually homologically mass minimizing. And I'll come back to that. All right, so this is a kind of general property. So the first real example to look at is the one that Robert was talking about this morning. So the first nice example and that's scalar geometry. All right, so I'm going to go back to just linear algebra. Let's let W be a real vector space. Well, this is a complex vector space. And I want to think of this as a real vector space with complex structure J. Okay, so I want to think of this complex with Hermitian inner product. So I have this almost complex structure J that maps W into W. This is a real linear transformation whose square is minus the identity. And I have a real inner product. This is a real positive definite inner product. Wow. Which has this compatibility property that JV JW is equal to VW. J is orthogonal for this inner product. Okay, and then, as Robert said, there's this associated Kähler form, omega, which on a pair of vectors, maybe I should make this, well, V and W, is by definition JV inner product W. Okay, and now this is skew symmetric. This is a real valued skew symmetric 2 form, which is positive definite. Okay, which is positive definite. Which is non-degenerate. Okay. All right. So now the claim is that this always has comass 1. Okay, so this is the Verdinger inequality that Robert referred to. Okay, and the statement is, let's let Q in W be any oriented real linear subspace, and I emphasize this is a real linear subspace of dimension 2p. So I guess I should just say Q is an element of, i.e. Q is in G2p of W thought of as a real space. Yeah? Okay. Then omega to the power p divided by p factorial has comass 1 applied to Q is less than or equal to 1, and equality holds if and only if Q is a canonically oriented complex subspace of complex dimension P. Okay. So in the words, in terms that I've been using, omega to the p is a calibration. I.e. omega to the p over p factorial is a has comass 1. And the set of associated phi planes is exactly equal to the complex Grassmannian of complex p planes sitting in the real Grassmannian. So here I'm emphasizing that this is the real Grassmannian, okay, the Grassmannian of real oriented 2p planes. So in fact, I guess I should just use this notation, omega to the p over p factorial is equal to 1. Okay, so this also has a fairly straightforward proof. It's just linear algebra. So let's take omega and restrict it to Q. So now I have a skew-symmetric form on a real oriented 2p plane. Okay, so now this, we have a real inner product line around, so this real inner product restricts here. When you have a skew 2 form on a real inner product space, then you can diagonalize it. Okay, because it's so this has a, so there exists, this is skew symmetric, so that means that there exists an oriented orthonormal basis E1 F1 up to EP Fp of the space Q, such that, well, we can draw the picture such that this, in this basis, the form decomposes into little blocks. If I got the plus and minus signs correct. And p minus lambda p. Actually, I think the minus should be here. so that omega essentially looks like this. If you want to write that out in terms of the basis, then that means that omega is of the form the sum from j equals 1 to p of lambda j ej star wedge fj star, where the e's and f's with stars on them represent the dual basis to the given basis, okay? So that's the same thing as saying this. And now, let's take this to the pth power. No, I'm sorry, this is omega restricted to q, of course. So if I take omega restricted to q and raise it to the pth power, well, these things commute, right? These are two forms, so they commute with each other. And so the only thing you're going to get are all the possible products where these are distinct, and they're exactly p factorial possibilities. All the various permutations of these terms will appear exactly once, and then you get lambda 1 up to lambda p, and here you get E1 star, F1 star, up to EP star, FP star. Okay? Well, this is the oriented volume form, because we chose an oriented basis. Okay, so this is p factorial, lambda 1 up to lambda p times the oriented volume form. And now, I can assume, by the way, in doing this, I can assume that lambda 2 is bigger than or equal to 0, lambda 3 is bigger than or equal to 0, up to lambda p being greater than or equal to 0, simply by, because I'm free to interchange the e's and the f's if I like. I can interchange all of them but one, right? All of them but one. And now, what are these lambdas? Well, lambda j is exactly omega applied to ej fj. By definition, this is I, right, times this vector, inner product with that vector. And now, this is certainly less than or equal to the Schwarz inequality, the length of these vectors. And these were orthogonal vectors, and j, these were orthonormal vectors, so their unit length in j is orthogonal. So this is exactly equal to 1. So each lambda is less than or equal to 1, and you get equality if and only if lambda, if and only if j of ej is equal to fj for all j. And that means precisely that this plane is invariant under j, and it's canonically oriented. Okay? So these numbers are all less than or equal to 1, and you're only going to get equality with 1 if this is true. Okay? It's very simple, but it has this amazing consequence now that so that's it. It has this amazing consequence that any complex submanifold of a Kähler manifold is actually homologically volume minimizing. So if I now go over to the Kähler case, so if suppose that, so now I have a manifold. Let's see, Robert had, well, we have the metric. I'm going to write it this way, and j and omega. Okay, so this is a Kähler manifold. A Kähler manifold. Okay, then you see that if I take the pth power of the Kähler form divided by p factorial, this is a calibration. Negative the p over p factorial is a calibration. Because the key condition to this being Kähler, given that you start with a complex manifold, is just that this form be closed. But now we see that it always has and if omega is closed, then any power of it is closed, right? Because d of omega p is p omega p minus 1 d omega. So this is 0. And so this is closed and it has comass 1. And as we've seen from this, the set where the associated set of planes is just so this is equal to the Grassmannian of complex p-dimensional subspaces, canonically oriented, sitting in G2P. I guess I used TX here, sorry. So here I'll emphasize that these are the real planes, oriented real planes, and these are the complex ones. And so the corollary is that any, so this means that the phi sub omega p over p factorial submanifolds, these are just the complex submanifolds, canonically oriented. And so any complex submanifold of a Kähler manifold is homologically volume minimizing. Okay. So when this is a kind of striking fact. So let me give you two simple examples. One is let's let x simply be equal to Cn with a parallel Kähler structure, the usual, just think of this as a vector space and parallel translate the metric at one point, or with a standard Kähler structure, standard inner product in J, and you get that any complex submanifold, if you take complex submanifold, maybe something that goes out forever or something that's contained in some domain, and take a compact piece on this, which has a nice boundary, then this is absolutely area minimizing. It has area. It solves the plateau problem. If you take any other submanifold with the same boundary, that submanifold has bigger volume. Well, if it had the same volume, it would have to be a complex submanifold, by what we've seen, because the things which actually saturate the bound have to also be phi submanifolds. And if it's a complex submanifold, and you have two complex submanifolds that have a common piece of a boundary, I mean, just if their boundaries, have some positive measure in dimension 2p minus 1, then they agree. You can't have two complex submanifolds having the same boundary in Cn. Okay? That's sort of the statement that a complex valued function, say in the upper half plane, which is 0 on the real axis, is identically 0. Or if it's 0 on a set of positive measure in the real axis, it's identically 0. Right? The real line is a determining set for holomorphic functions. And boundaries of complex varieties are determining for the things that they bound. So these are unique solutions to the plateau problem for the boundary. And of course, it's easy to write down these things using algebraic equations. But another interesting case is the the case of projective space, so if X is equal to complex projective space, then I remind you that the 2p homology group of X with integer coefficients is just the integers, and it's generated by the class of a linear subspace of dimension p. Okay? And so now there are lots and lots of compact complex submanifolds in projective space. They're all defined in homogeneous coordinates by homogeneous polynomial equations. Okay, so it takes no imagination to write down tons and tons of these things. But the interesting thing is that if you have two, so now if I have M and M prime, compact complex submanifolds. Well, let's let M be a compact complex submanifold of Pn with no boundary. Okay, then when you say that M is homologically minimizing, it's not just there is no boundary, but it means that if this is M and I have some other M prime with the property that the two represent the same homology class, okay, then the volume of M prime must be bigger. So the volume of M is less than or equal to the volume of M prime for any prime in the same homology class. So if I have another oriented 2p dimensional submanifold of, say, class C1, whose homology class is the same as that of M, then I have this inequality. So you can now think of the plateau problem as taking place in the homology class. Find a representative of least volume in the homology class. And when you have a complex submanifold, an algebraic variety in projective space, it always satisfies this problem. But we know more. We know that this inequality is saturated only by other complex submanifolds. And there are many of them. Many, many of them. Okay? I mean, all you need to know, if you look at the hypersurface case, then you get one every time you write down a homogeneous, for every homogeneous polynomial of degree d, you get one of these, well, for almost every, you get a submanifold of codimension 1, which is smooth and represents the homology class d times a hyperplane. And so another thing that you see is that the homology class determines the volume. So all these submanifolds of degree d, even though they have, well, they're generically all diffeomorphic, but they can look very, very different because you can take them and move them by general linear transformation. So they may look very round, like a Fermat hypersurface when you first define it, and then you hit it with some general linear transformation that just squeezes it. So all these interesting cycles get pushed into a little tiny ball, but the thing still has the same volume. You know, and you can take this thing and squeeze it down so it's in a small neighborhood of a hyperplane. But no matter how you push it around in projective space, it always has the same volume. It's kind of interesting. All right. So now, let me give you one other interesting case of calibrations which looks very, very different. So I want to look at foliations. So suppose I have a Riemannian manifold, and on that manifold I have a foliation of codimension 1. So X is, as always, Riemannian manifold of dimension n plus 1. And let's let F be a smooth, it only has to be C1, smooth codimension 1 foliation. So I remind you, a foliation is a decomposition of the manifold into submanifolds with the property that at any point you can always find local coordinates so that the submanifolds are given by setting the first coordinate equal to constant. So these submanifolds, they may wind around a lot, but this decomposition into mutually disjoint submanifolds has the property that locally you can always find a coordinate chart so that these manifolds are the level sets of one coordinate function. Okay? So every time you have a non-singular vector field, the orbits of the flow give you a one-dimensional foliation. And I'm going to assume that the foliation is oriented. And then, so assume F oriented. So oriented means it's orientable. Well, the tangent planes to the leaves are orientable, and I've chosen an orientation globally over the manifold. Well, I mean, the whole tangent bundle to the leaves has to be orientable, and we've chosen an orientation. Okay, so then I can let phi be equal to the unit volume form of F. So what do I mean by this? Well, you can take the unit normal. Well, we have a metric here, so we can identify tangent vectors and cotangent vectors. Okay, so let's let locally. I can choose E1 up to En, an orthonormal frame field for the tangent bundle to F. So I just choose vector fields E1 through En, which are orthonormal and are tangent to the foliation. Okay, then phi is, this should be an oriented orthonormal frame field. Then phi is essentially E1 up to En. So maybe I'll say it's equal to the Riemannian duals of these, and I'm going to think of this as E1 up to En. Okay? So here's a form that manifestly has comass 1, because this is really just the Hodge star of a vector, namely the normal vector. This is simply the Hodge dual of nu, where nu is equal to the unit normal. Okay? The unit normal. And so so clearly I claim the comass of this, which is equal to the inner product of E1, En. See, every vector is simple, right, in this case. So maybe I should just point out, in codimension 1, every vector is simple. There's nothing interesting about wedge 1 of the space. Wedge 1 of the space is the space, and wedge n and the codimension 1 forms are just the same. So this is exactly the same as the L2 norm, and that's 1 everywhere. Okay? This is a unit simple vector. On the other hand, I claim, well, maybe I'll make this a lemma. If you take the derivative of this, the exterior derivative of this form, you're going to get a form of degree n plus 1 now, top dimensional form. And I claim that this is simply minus h times the volume form of x. We call this manifold x, right? In other words, it's minus h times E1 up to En wedged with the normal, where h is the mean curvature. In other words, at any given point in the at any given point, this is a hypersurface, and it's a submanifold of a Riemannian manifold. It has a classical mean curvature, the sum of the principal curvatures, the trace of the second fundamental form. Okay, and I claim that that if you, so it's a very simple fact, you take this unit volume form, take the exterior derivative, and you get the mean curvature times the volume form. Okay? What this means, of course, is that this is a calibration if and only if all the leaves are minimal. If all the leaves are minimal. So what's the proof? I'll do this quickly. So let's take, what is d phi? Well, one way of writing down the exterior derivative is like this. You take covariant differentiation with respect to the Riemannian connection and then follow it by wedge product. But you have to do it over a full orthonormal basis, so we also have to have here nu wedge del nu of phi. Okay, now phi is just the wedge product of these forms, so this becomes the sum over j and k of ej wedge. Now, the exterior derivative is the derivation of exterior multiplication. So this becomes E1 wedge del Ej of Ek En. And here I get nu times the sum, nu wedge, the sum of Ej wedge E1, and then del nu of E. No, what am I saying? Yeah, nu. Yeah, sorry. Nu wedge the sum j equals 1 to n, j equals 1 to n of E1. And then here we get the derivative of the jth term up to En. Okay, now what happens when you take this derivative, when you take this covariant derivative? Well, you can expand it in terms of the orthonormal basis given by the e's and the normal vector. But, I mean, first of all, look at what we've got. We have almost all of the e's appearing, so that if Ej is not equal to Ek, then you're taking the wedge product with Ej someplace else, and that's 0. So the first thing you see is that this is really the sum over j of Ej wedge E1, and here you have Ej of Ej. You just get the diagonal terms. All the other terms are 0 because of exterior algebra. And now the same thing is true here. This is going to be a sum of, now let me expand this out. This is going to have components in the this is going to have components in the directions Ej, but the only one that's going to count is the one which is in the Ej direction, because all the others are going to be multiplied. When you expand it in terms of an orthonormal basis, all other terms will go to 0, as will the normal term. So here we're simply left with I guess it'll be a sum E1 wedge, and here we get del nu Ej times Ej, and then on you go. You only get the jth term. Okay. And now, again, what you see here is all the tangent vectors. So all that's left is the normal component. All that's left is the normal component. And the normal component can be written as, well, that's essentially the second fundamental form. So this then becomes the sum of del Ej on Ej, dot product with the normal vector. And now there's a minus here. So I take the normal component, and then I slide it to the front, and I slide Ej into here. And so I've moved this past j minus 1 vectors. I moved this past j minus 1 vectors. But I had to interchange these two, so I get a minus sign. And here I get nu E1 En. And here, well, this is 0. I mean, del nu of Ej is simply 1/2 the derivative of the length of Ej, and that's 0 because this has constant length. Okay? So this is 0. And this is exactly the trace of the second fundamental form. The second fundamental form is gotten by taking two tangent vectors, extending them to local tangent vector fields. Oh, take the covariant derivative, take its normal component. So this is exactly H. So I'll just say that this is equal to H by definition. Trace of the second fundamental form. Okay, so it's an easy calculation, but it has a very nice consequence. Namely, so for example, I mean, how do you get a foliation? Well, first of all, it gives you some negative results. So if you're given a foliation, you could ask, is there a metric on the manifold that makes all the leaves minimal? You know, that would be pretty. And one thing which comes out of this is that that's impossible if you have any compact leaves which are homologous to 0. Because every compact leaf, so if H is identically 0, note that every compact leaf is homologically volume minimizing, and in particular and therefore it's not equal to 0 in Hn minus 1 of x. Right? Even R. So if you have a leaf that's homologous to 0, then there is no Riemannian metric that makes all the leaves minimizing. So if F has a compact leaf homologous to 0 over R, then there does not exist a metric making every leaf making F minimal, making H identically 0. Every leaf minimal. Okay, but there's a nice case where you can construct foliations of this kind. So we just do the following. Let's take a domain in Rn, and F a real valued function, and assume that the graph of F, I'll call it GR. These are the in omega cross R. Well, let me just put it in Rn cross R. X is in omega. Assume that this is minimal. Hypersurface, by which I mean the mean curvature is identically 0. Okay, so most of you know that this translates into a certain quasi-linear elliptic equation on the function f. Okay, it's not quite that it be harmonic. It's more complicated and more interesting than that. We're going to see this tomorrow in a more general case. So so it means that this satisfies the minimal surface equation. Now, where do you get a foliation? Well, it's very easy. Here's the domain in Euclidean space. And now let's look at omega cross R. And this is foliated. Here's the graph. Now you just translate the graph. Right? Just look at the graphs of f plus a constant. Okay? It's foliated by the graph of f plus c for c and r. And they're all minimal. The translative of a minimal surface is minimal. So you now have this foliation. So these things are actually homologically minimizing. So for example, if the domain is convex, you can show that that means that these things are actually solutions to the absolute minima for the plateau problem. There is no better solution, even if you add handles. And the interesting fact is that you can do this. The really interesting case is when omega is all of Rn. So now if you have a function which is defined over all of Rn, and it satisfies the minimal surface equation, then the graph of f is homologically volume minimizing, but there is no homology. So therefore, absolutely volume minimizing. And sort of using this fact, I mean, you get insight into something called the Bernstein theorem, which says that in the case that n is equal to 2, in fact, it works all the way up to n equals 6, I guess. Any such function defined over all of Rn, which satisfies the minimal surface equation, is actually a linear function. Okay? But then there are examples of interesting solutions, global solutions, in dimensions greater than that. But a very key point in the proof of this Bernstein theorem is the fact that a graph is always really minimizing among all possible competitors. Well, certainly among all C1 submanifolds. Now, what I was planning to go into for a little bit, but I won't have time, which is probably a great relief to most people, was to talk a little bit about currents and rectifiable sets. But we don't really need to do that. But I'd like to at least make the point that that everything we've been saying here starts with a smooth form and then looks at submanifolds. But these submanifolds, there's no reason why they couldn't have singularities, right? I mean, the conditions we've made on them have been rather mild. And in fact, in the complex case, you can really allow them to have the standard complex singularities, and everything goes through. So it's not so difficult to see that a complex subvariety, that's something locally defined by vanishing of holomorphic functions. So cut out by a certain number of holomorphic functions being equal to 0. Any such thing has the property that the Hausdorff measure of its regular points is locally finite. So you've got this thing which is singular, but if you just look at the regular points, even in the neighborhood of a singular point, the regular points have finite Hausdorff measure. So over any compact set, a complex analytic subvariety gives you a submanifold of finite volume. And such creatures, and so now such creatures, in fact, can also be shown, if you have such an analytic variety, you can show that the sort of weak boundary of a complex analytic subvariety is 0, by which I mean that if you integrate the exterior derivative of a form over the regular points, this is 0. And that's really, and so integrating a differential form over the regular set makes sense, and you can talk about homology. So the argument that I went through for Vertinger's inequality and the fact that complex submanifolds are minimizing actually applies to analytic subvarieties. The singularities do not enter. And so you can replace everything I said about complex submanifolds of a Kähler manifold with complex analytic subvarieties, and it's still true. And you could also replace not only complex analytic subvarieties, but you could look at sort of locally finite combinations of analytic subvarieties with integer coefficients, which is a natural thing to get. I mean, if you start with submanifolds and you sort of look at limits of them, then you get submanifolds with multiplicities in general, because several sheets may come together. They also are minimizing, but now they don't minimize volume, they minimize weighted volume. You have to count how many sheets you have, okay? And this all carries over to calibrations. So for calibrations, you can talk about quite general objects, and the general objects are rectifiable currents. So a rectifiable current is sort of a weighted integer combination of rectifiable sets. And rectifiable sets, well, maybe I can at least give the definition. A set is said to be rectifiable in dimension P if it can be written as a disjoint union of measurable subsets, Hausdorff p-dimensional measurable subsets. So this is a disjoint union with the property that the Hausdorff p-dimensional measure of this set is 0. So this is up to sets of Hausdorff measure 0. And every EK is contained in a C1 submanifold of dimension. This is all going to be in dimension P. MK. This is a C1 submanifold of dimension P. And here I'm always going to assume that the whole set has finite Hausdorff measure. Okay, and this makes sense on any Riemannian manifold. Now, when you have such a thing, it turns out that this is really the right generalization of submanifolds. So it includes, take a C1 submanifold and take some Borel subset of it. So for example, a Cantor set on a curve. Or you can do something really weird, like in the plane, take all points with rational coordinates, and at the kth rational coordinate, take the circle of radius 1 over 2 to the k. Okay? So here's something which is dense, right? But it has finite Hausdorff measure, and it's a union of manifolds outside a countable set, actually. Okay, so these things are quite general, but one of the nice things about them, there are two nice things about them. The first is that they have compactness properties. Okay, this is a deep fact, but if you bound well, they have compactness properties when you pass to sort of locally finite sums of these guys. So if you bound the mass and bound the support, then every sequence has a convergent subsequence to a rectifiable set, a generalized rectifiable set. These guys also have tangent planes at every point. And so so in some sense, they really look like manifolds. And rectifiable current is simply something which is made up of rectifiable sets, each of which has assigned to it an orientation. And when you have such a thing, then you can go through exactly the argument I went through for calibrated manifolds and talk about phi rectifiable sets and phi rectifiable currents. These are rectifiable sets with orientations, and these are finite. These are sort of countable sums of these, and so it turns out that every phi rectifiable current for a calibration is also a solution to the plateau problem. And currents which are solutions to the plateau problem were proved in a very deep theorem of Almgren to be manifolds outside a set of Hausdorff codimension 2. Okay, and then there's an old compactness theorem of Federer that says that these things are compact, and as a result, if you want to look in a compact manifold at all the phi submanifolds in a given homology class, that's a compact set. The moduli space is always compact. But you have to sort of pass out of the realm of submanifolds and get into the realm of these more generalized things which have singularities. Okay. All right. Thank you very much.